didn't bring it from the reception.
Well, I can do it all.
Yeah, so let's keep going. Okay, so we'll continue, and Olaf will now give his. This is your third. Yeah. So, like I said.
Yeah, okay. Well, yesterday I gave you some exercise. I just want to ask, did anyone try to compile this code, and were there any problems? Or you didn't try? Yeah?
When I compiled it, I ran it, I don't know what the results would be.
Okay. Well, it was nice from Rob to talk about the polyacopy. So one of the results is to get the polyacopy. So I told you that in Monte Carlo we generate a sequence of configurations, and for each configuration we measure these quantities, the plaquette value and the polyacopy. And first of all, you can look into the time series of these observables, so configuration by configuration, and see how your distribution thermalizes. And then, of course, you can make a long run and calculate expectation values, for instance, of the polyacopy, and try to reproduce what Rob showed in some. For instance, you can try to understand how you see the deconfinement transition, how the polyacopy changes from small values to large values, where this critical beta value or critical temperature is. Maybe I should say some words about this input file that you need there. So there you can set the parameters of the calculation. So the first line is just the lattice size. So in this example here, it would be 8 cubed times 4. So 8 points in the spatial direction, 4 points in the temporal direction. And the second value is the beta value. The status means that's the status for the random number generator. So you need random numbers for this Monte Carlo. And either you can start or initialize this random number generator with a random number, or you can read in the state of the random number generator that you used before. If you start the program again, you maybe want to continue this random number generator, and then you have to put in 1. And that's the file where the status of the random number generator is put into. This flag load, it's set to 0. Then you start with the unit configurations where all gauge fields are equal to 1. If you take 2, then the gauge fields will be random. So each SU3 will be random SU3 matrix, and 1 is used to read in an old configuration. So if you let your program run for a very long time, you may stop in between, save your configuration, and start with the configuration again. Okay. And that's just, this here's a flag to save the configuration. So 1 means you save the configuration at the end of the run, and 0 means you don't save it. The same here for these measurements. So here, all the polyacopy will be written into a file, and PL will be plaquette values. Then NO start, that's a parameter for thermalization. So usually at the beginning, when you start, let's say, with the unit configuration, you need some Monte Carlo steps to get away from this one and thermalize your distribution. So usually there we take around 1,000 or 2,000 updates to decorrelate the configuration and to get into a thermal equilibrium of these Markov processes. And then this 100 here, that's then the number of real updates, where after each update your observables are measured. With this flag update, you can switch off the updates. If, for instance, you just want to read in one configuration and measure your observables without doing some updates. And the seed here is the seed for the random number generator. So this input file you need, and you have to change it if you want to have a different lattice, let's say, or different beta values. Yeah, so any other questions about this? Well, then if you like, you can just try it and do some lattice calculation with this. I will now come back to physics. And what I will discuss today is spectral properties and transport properties in the quark-gluon plasma. Do I have a pointer here somewhere?
Yes.
Okay, so what we are interested in here is to understand a bit more about the quark-gluon plasma and also to determine quantities which are also measured in experiments. So this will relate to thermal dilepton rates. Dilepton rates are proportional to the vector spectral function, so we need to calculate this vector spectral function, and then we can estimate the thermal dilepton rate, let's say at one temperature, from this equation here. The same holds for the thermal photon rate. There we also need the vector spectral function, but there we need it at a frequency omega equal to momentum, and this gives us the photon. The other quantities that are also encoded in spectral functions are transport coefficients, two formulas. So one example is shown here, that's for the diffusion coefficient, for example for the diffusion coefficient of heavy quarks. Then you have to take a limit of the spectral function divided by omega, limit omega to 0, and then you can determine this transport coefficient. So what we need to determine are these vector meson spectral functions, but on the lattice we cannot directly calculate them. What we can calculate are hadronic correlation functions, and then we need to do a spectral reconstruction to get from these correlation functions to the spectral function. And what the problems are in this spectral reconstruction I will discuss in quite some detail in this lecture. So what is the motivation for all of this? So one of the motivation is to understand the low mass enhancement seen in the dilepton rates from experiment. So here's a Phoenix, a quite old Phoenix example, where you see here a cocktail and the results for heavy iron. You see an enhancement of this dilepton rates here in this low mass region, and this could be explained by contributions coming from the QGP, and that's why it's so important to understand this dilepton rates of the spectral function in the QGP. The same for the thermal photons. So photons and also dileptons, they are produced in all stages of a heavy ion collision. So in principle, you also need to understand the whole evolution of the system. So you need to have a model, hydrodynamics, a fireball model, or whatsoever, to understand the whole evolution of the system. And then you can use spectral functions at different temperatures to combine it with your model and then integrate the whole evolution. And then you would get these dilepton rates, or also photon rates. So photons come from all stages of this expansion of the system, but there might be one region where the photons from the QGP may give at least a very large contribution, and therefore it's important to understand what this contribution could be in the QGP. Well, the motivation for determining transport coefficients in the plasma is, for instance, to understand the RAA or PQ of heavy flavors. And therefore, for heavy quarks, people do transport models for heavy quarks in the medium, and then within these transport models, then determine or match these transport models to experimental data. And in this way, rather indirectly determine or tune the transport coefficients in these models to describe then the experimental data here, for instance, for RAA and P2. There's also some old plot just for motivation. We have seen on one poster over there very new results for this, and also comparisons to much more models. But in all these models, I think on the poster, these transport coefficients are tuned to describe the data. What I will argue is that we really need to determine these transport coefficients from QCD using first principle lattice calculations, and then use them in these models to improve on the models and also to test the validity of these models. So that's the motivation for getting transport coefficients. So as I said, all these physical quantities, dielectrons, photon rates, transport coefficients, they are all encoded in the spectral function. This we cannot calculate on the lattice. What we can calculate are hadronic correlation functions, like here. And then we need to, and these correlation functions are related to the spectral function through this integral equation here, where you have this kernel here, which you multiply with the spectral function, and then you have to integrate over omega, or frequency energy. And these spectral functions are continuous functions, while on the lattice we can only calculate correlation functions at some temporal distances tau, so that's the order of I don't know, 10 to 40 data points that we get here for the correlator, while we want to have a continuous function rho. So that's usually called an ill-posed problem, because there are infinitely many spectral functions that describe the same correlator as within arrows, and it's hard to do this inversion, for instance, numerically. Furthermore, there are many contributions, many different scales entering in the spectral function. That's shown here. So there's a continuum at large frequencies. There may be possible bound states and intermediate frequencies. So for instance, if you think of heavy quark bound states, they might persist in the quark-gluon plasma, and they may melt at some temperature. So one also wants to understand this region of bound states. Then there are transport contributions at small frequencies, usually modeled by Wigner ansatz, which is well, or which comes in principle from hydrodynamical arguments, which work at a very small omega, and they predict such an ansatz for a transport peak, which then in the limit of omega to 0 gives this transport contribution. And in addition, you have cutoff effects on the lattice, and they are mainly at large omega, but you have to get rid of these cutoff effects, so you have to take the continuum extrapolation of these correlation functions to at least remove this effect in the spectral function. And right, so there are many different contributions in the spectral function that you all in principle have to take into account. So what we need are large lattices and continuum extrapolations to have a large number of data points for the correlator, a large number of distances. This at the moment is still only possible in the quenched approximation, so all the results that I will show in this lecture are done in the quenched approximation. But for these quantities, the quenched approximation is already quite a good approximation. So if you, even at zero temperature, if you calculate, for instance, masses using such correlators, you see an effect of around 10% switching on dynamical quarks. So the quenched approximation here is quite good. And then what I always will argue is that we need to constrain the spectral function at large energies. So at large energies, due to asymptotic freedom, perturbation theory works at some point, and you can use perturbation theory to constrain the UV behavior of the spectral function, and then model the low omega part of the spectral function by some ansatz, which is physically motivated, and in this way try to invert this integral equation at vector spectrum.
Question.
Yeah.
Why for so much large temperature it's linear behavior for spectral function?
Sorry?
At temperature equal infinity, it's linear behavior for large energies. Right?
You mean this rise?
Yes, yes.
Well, that you can calculate in the non-interacting limit. There you can calculate the spectral function for these operators, and there it goes like omega to the power 2. That's just in principle due to dimensional reasons. But this is a very large contribution. If you look a bit closer into this kernel here, you will see that this large omega part in the spectral function, that gives many contributions at small distances in the correlator. That gives a very large contribution there. We will also see that later on. So it's really important to understand this large omega part, and I would always argue to use perturbation theory at least in energy regions where it's possible. Okay, maybe I should say some word what these correlators here really are. So that I will do on a blackboard. So what we do, what we want to calculate are correlation functions which are shown there, like some operator at some point, let's say spatial point x and t, and some other operator at spatial point 0 and temporal point 0. And this j we are looking into meson correlation functions. So this j then, say the j of x comma 0, that is psi bar x comma 0, and then you need some gamma function to project on the state you are interested in, psi 0 t, comma t. Okay. So it's a quark-antiquark pair where you put in here the gamma matrices, and if you choose, let's say, a 1, you have a scalar to describe the quantum numbers of the scalar meson. If you have the gamma 5, you have the pseudoscalar on the PS. Or the gamma mu, you have the vector, or gamma 5, gamma mu would project on the axial vector. So in this way you can project onto different states, different mesonic quantum numbers. What I will mainly talk about in this lecture is the vector meson, where this gamma is gamma mu. And then we calculate these correlation functions here. And so these are here point-point correlators. So you need a dagger somewhere. So you construct your meson operator at one point in space, let's say 0, 0. And you destroy it at some other point xt. So let's say here is 0, here is x. And then what you get here are quark propagators that go from one point to the other. And this gives you the meson operator where you construct the meson at some point and destroy it to the other point, and you look into the distance dependence of this correlator. And then what we usually do is we make a Fourier transform here and integrate out the spatial part here by a Fourier transform in spatial x and spatial momentum, and then you get a correlator which then depends on the temporal distance and on the spatial momentum. Okay? Right. So what you have to calculate for this, or in the quantum field theory, is a quark propagator, and the quark propagator is given by the inverse of the fermion matrix. I haven't introduced the fermion matrix on the lattice here, but it's the same for all discretizations. You always have to calculate the inverse of the fermion matrix at some point, in this case 0 and x, and then you have to combine this inverse, which gives one quark propagator, with the other quark propagator, put the gamma matrices in front of there, and then you can calculate this correlation. Inverting this fermion matrix here, there you can use standard inversion methods like a conjugate gradient or improved inverters to invert this fermion matrix. So that's how these correlation functions are really calculated on the lattice, and then you get this momentum dependence and the t dependence for the correlation. Okay. So In the first part here, I will set this momentum here to 0. But later on, we will also look into correlators for non-zero momentum, which then are related to the photon rates. So first, I will discuss the case for the dielectron rates. So what we have done is we have generated a large number of quenched SU3 gauge configurations. In principle, with a similar program that I gave you. In principle, you could calculate these gauge field configurations even with this program. But it will take some time. So you see the largest lattice that we have there is, where is it? 192 cubed 64. So that's quite large. This will even not fit into your into the memory of your laptop. And running the program on a very small lattice on your laptop, you can estimate how long it will take to generate such a configuration. The computing time just scales with the volume, so you can do some run on your laptop and then estimate how long it would take to generate such a large configuration. These gauge field configurations are separated by 500 updates because we want to have them uncorrelated, and that's very important. Do not have any autocorrelations in this generation of the gauge fields. What we then use to calculate these operators here, the inverse of the Fermion matrix, there we use so-called non-perturbatively order A Clover improved Wilson fermions for the valence quarks here. And we did that in the quenched approximation. So what does this mean? In principle, you have so between these quark propagators, you have the interaction. Like you have interactions with the gluons. So if you think of it that perturbatively, you can have any interaction, gluonic interaction here. But you can also have virtual quark loops in here. And what we do in the quenched approximation is we forget about any dynamical C quarks here, so any quark loops in this game, and only have a gluonic medium, which gives then the gluonic interaction between these two valence quarks of the object. Okay? So we put these valence quarks in a gluonic medium and then calculate the effect of the medium on these objects. Okay. So we needed these large lattices first of all to get a large number of points in the temporal direction to do the spectral reconstruction. And furthermore, we have 3 different lattices for each temperature to then also perform a continuum extrapolation. Typical correlators you see here, so they show exponential decay. Here you see the result on the finest lattices for 3 different temperatures compared to a free non-interacting correlator. And at least on this scale here, you don't see any difference between all these results, and all seem to agree even with a non-interacting correlator. But that's mainly due to this large scale that we have here. So to see really the physical effects, we always normalized with this free correlation function. So that can be calculated analytically, and then we normalize these correlator by the free correlation function. And that is, for instance, shown here. So here we have at one temperature of 1.1 Tc, 3 different lattice correlation functions, normalized now by this free correlator, and also normalized by the quark number susceptibility. And that is to get rid of any renormalization here, because in principle you have to renormalize this correlator, but you have to renormalize this correlator in the same way as the quark number susceptibility, and therefore any renormalization drops out in this ratio. So then we have 3 different lattices, and here you also see the continuum extrapolation. But first of all, you see that there is a difference to the free correlation function. So it seems to approach a value which is given by 1 over quark number susceptibility, which is around here, I think 1.2 in this case. So at small distances, this ratio G over G3 becomes 1. That's due to asymptotic freedom. So if you go to very small distances, you have asymptotic freedom, and your correlator, your non-interacting correlator, should become a free correlator at some point, at least asymptotically if you let the distance go to 0. But then at large distances, you see deviations which even go up to 80% compared to the free case. This continuum extrapolation that we do here, that we do always at fixed distance. So let's say here at point 2, we take then 3 values here of our lattice correlators, that's shown here, and then to the limit of 1 over nt squared to 0, which, as I explained to you, is the same as doing the limit of a squared to 0, so lattice spacing to 0, and then you can read off the continuum value of the correlator here for 4 different distances, and that gives here this band as the continuum. Okay. So the effect is not that large, but it's important to get rid of these cutoff effects that you see here and really to perform the continuum extrapolation. That's the same, but for another temperature. Also here you see the cutoff effects become larger at small distances, so here it's really important to perform the continuum extrapolation, while here the effect is a bit smaller, but it's really important to do this. And then we have well-defined continuum extrapolated correlators, and then we can use this to do the spectral reconstruction later on. Same for 1.5 TC. Well, the quark number susceptibility, we also have to take a continuum limit here, and then you can compare the continuum extrapolated correlators now without this quark number susceptibility in here, so just the non-perturbative the lattice correlator, continuum extrapolated, divided by the free correlator. And here you see that there is not much temperature dependence in this temperature regime between 1.1 and 1.5 C. So this is already an indication that the dilepton rates are rather temperature independent in this region. And we will also see that the transport coefficient is more or less temperature independent in this region. So that's already indicated here in these correlators. And now we want to go to the spectral function. And well, there was already the question how the spectral function looks at infinite temperature. So at infinite temperature you have a non-interacting system, and you can calculate this so you have no interactions here, and you can calculate this correlation function and also the spectral function analytically. And that looks like this. So this is for the vector correlator. There we have different components. So the 0, 0 component, that in the free case is just a delta function, while in the spatial polarization you have this term here, and here you see this omega squared behavior at large omega, so that you already get in a non-interacting case, and then you have a temperature dependence here at small omega. This delta function here, that cancels exactly if you take the sum of these two, where you have to take a minus sign and it's 0, 0. So the full vector spectral function is this, which then only contains this omega squared. So if you now switch on interactions, this temporal component of the vector correlator, that is protected and gives you the quark number susceptibility times the delta function. So the correlator, if you do this integral of the spectral function with the kernel and calculate the correlator, then the correlator in the 0, 0 component is just a constant, which is proportional to pi cubed. In the spatial part, this is different. So there the delta function is no longer protected, but gets veered out into interactions. And a simple answer is to take a pi Wigner here, which is like transport peak that one can argue, for instance, from hydrodynamics. The large omega part here, that then becomes perturbative. You can calculate that in perturbation theory. And in leading order perturbation theory, this just gets a correction here, 1 plus kappa, where this kappa is alpha s over pi, and in principle you have to take a running coupling, of course, here into account. But we use this here as a very simple ansatz to describe our data, where we just take a Breitbiegner here with two parameters, so a constant and the width of the Breitbiegner, and we keep this, for the moment we keep this kappa here fixed to a constant. So then we have three parameters, and in addition also the program susceptibility in principle. And once we fit this ansatz here to our correlation functions, then we should know all these parameters, and we can, for instance, calculate the electrical conductivity out of these parameters. So we have to take this limit here, and this just depends on the parameters of this fit. So that we did. So we took our continuum extrapolated correlator, that's here for a temperature of 1.1 Tc. Then we took this very simple ansatz, plug it in here, and then fit it to our continuum extrapolated correlators. And you see this describes the data perfectly. The chi-squared over degree of freedom is around 1 here, and then we get results for electrical conductivity and for all these parameters in our. Okay. So you might say, no, well, that's fine, so let's just believe this, and that's the end of the story. But we knew that, or we know that this integral equation is very problematic, so you can construct other spectral functions which equally well fit this data. So we wanted to analyze the systematic uncertainties in this ansatz to understand not only the fit error here, but also the systematic uncertainties in all these parameters. So we varied this ansatz a bit. First of all, we modified the large distance behavior in such a way that the contribution at small omega is removed, because at small omega you have this transport peak here, and you shouldn't have in principle the free or alternative part here, but that should dominate the large distance. So we have truncated this large omega behavior by a smeared step function, and here you see different spectral functions which all fit our data perfectly by changing this ansatz. And in this way you get some systematic uncertainty here for the transport coefficient by varying this ansatz here. All these spectral functions that you see here within errors, they all describe the data perfectly. Then one of the big questions is always, do we really have a real transport peak? Do we have a Breitbiegner at small omega? Or could it also be that the spectral function is rather flat? Okay. This question is a bit related to discussions about strongly coupled system, because if you calculate the spectral function in strongly coupled systems like in ADS-CFT, you will never find a transport peak because you have no quasi-particles in the game, and they are related to this transport peak. So in ADS-CFT, people find such a flat behavior of the spectral function, and we wanted to study if we can also describe our data by such a flat spectral function. So we have constructed an ansatz which is rather flat, but which contains the correct perturbative behavior at large omega, and then again fitted our correlators. And also this ansatz describes the data perfectly with a chi-square of 1. So then we have different ansätze. We even wanted to improve more on this by improving the large energy part of the spectral function. So far we just took the leading order perturbative part, even without the running of the coupling. So we wanted it to improve on this UV behavior. And at very high energies, due to asymptotic freedom, perturbation theory should be working fine. And even at very high energies, thermal effects should be suppressed. So you have vacuum physics at some point. In the vacuum, you can calculate the spectral function up to very high order. It was done up to 5 loop order. So this R of omega here, that's a series in alpha s, up to alpha s to the power of 4. Then we also use the 3-loop running of the coupling. And well, you have to use some proper renormalization scale to compare the perturbative calculation to the lattice calculation, then we use the maximum of pi t omega, because at smaller omega perturbation theory shouldn't work, so you have a scale which is somehow a larger end. And then, in addition to this vacuum perturbative part here, we also then use the leading order thermal effect, take that into account. And well, in this plot here, the transport part was just taken as a delta function, but this plot here just shows the effect of different loop orders in the perturbative series, and there you see that it seems to be enough to go to order S3 or so, but we took even alpha S to the power 4. But you see a convergence of this series, at least at small distances. At larger distances, the effect becomes a little larger. So then we used this 5-loop vacuum plus the leading order thermal correction in our ansatz. Then we also took the Breit-Wigner at small omega and then fitted this to our continuum extrapolated results. So this gives then a third spectral function which also describes perfectly our data. And from all these three, we somehow get a range here for the spectral function in the low omega limit, where this flat behavior is somewhat at the lower end. So we have also changed this ansatz a bit, but we never get below this flat behavior. And the perturbative ansatz gives somehow the upper limit of this. But all these three spectral functions here describe the data with a chi-square of order 1. So they are somehow equally well compared to our data. And this now we use to estimate our systematic uncertainty. And then we get in the limit of omega to 0 from this ratio, the electrical conductivity in this case for the light quark sector, and the results you see here. So the errors are quite large. But there are really the systematic errors that are in the game here. And we were very happy when we got this result. At least we could give a lower and upper limit for this electrical conductivity. And within these large errors, we don't see much of a temperature dependence here, but that was already indicated by looking just on the corridor. We can compare this now to different other lattice calculations. So the red points here that are our estimates. So they are done in the quenched approximation, but continuum extrapolated. While all the other results here are not continuum extrapolated, but they contain dynamical quarks, although not physical, but rather large quark masses. What they see is that the electrical conductivity gets smaller if you come close to TC, so that is expected. What they then see is that it even drops further below the critical temperature. That at least I don't really understand, and that also comes out differently in different other models. We will compare this to calculations in platonic transport approaches, and we had one poster where this was discussed in much more detail. And in most other approaches, you see that the electrical conductivity rises again at smaller temperatures. So this really needs to be understood, so these lattice calculations need to be improved, mainly around TC and below TC, and that is something we want to do in the future. But nevertheless, there is really progress in determining transport coefficients, although the systematic uncertainties are still large in the lattice calculations, but also large in other approaches to determine. Now that you have the spectral function, you can take the full spectral function and plug it into this formula here to calculate the dilaton rates, and the result is here for the three different temperatures, which agree quite well. It goes into the Born limit at large energies and is comparable to half thermal loop at intermediate energies, but then it has better behavior, let's say, compared to the hard thermal loop, because the hard thermal loop calculation cannot really be applied at small energies, because it's a perturbative calculation, although we do something there, but it shows some of the wrong divergence here and would give infinite electrical conductivity. Well, we get a finite electrical conductivity which dictates this behavior here and so on. And these results now in principle you could put into your favorite model that describes the evolution of a heavy ion system of your medium and try to estimate from that at least the contribution coming from the QGP in this temperature. Okay, before coming to the photon rates, maybe are there some questions here?
I mean, when you have shown these two figures for the conductivity, this which was showing up is normalized to the temperature. The right-hand
Yes,
side is not normalized.
they are right. They are both normalized by temperature.
Both are. So there was no.
Right.
Okay, thank you.
Other questions? Well, then we go to the photon rates. So what we need there is the spectral function, in principle not in the full omega region, but only at the photon point where omega is equal to momentum. So there we calculated the momentum dependent correlation functions for a few momenta. And then we also used perturbation theory in the large omega part to constrain the spectral function for the spectral reconstruction. There are a lot of perturbative calculations for spectral functions or photon and also dialecton rates. Order ones for leading order, leading log order, and so on. But there was a lot of progress also in the perturbative calculation of these quantities, where at least at some invariant regions of invariant masses now next to leading order calculations were done. And at very high energies you can again use vacuum perturbation theory and go to quite large order. Okay. But these perturbative calculations are always done in some limits and some energies, some invariant masses. But what we need is at different energies, so we use an interpolation of these different perturbative calculations as an ansatz for our spectral function in the perturbative region. Then for the low omega part of the spectral function, so I've always argued that there you have, for zero momentum, you have this Wigner, which you can determine from hydrodynamic arguments. Also for non-zero momentum, you can use hydrodynamic, at least in the regime where omega and k are small compared to alpha s squared times temperature. And there the vector spectral function looks like this. So there you have the momentum dependence, the diffusion coefficient enters here, squared, and also the quark number susceptibility enters here. So again, the quark number susceptibility, that just comes from the zero component of the vector. The diffusion comes from the Kubo formula. And this diffusion coefficient, that is related to the electrical conductivity that I showed before. So there you also need to know the quark number susceptibility. Right. It's a bit surprising that, well, it's not really surprising, but it comes out that in an AES-CFT framework, the vector spectral function has the same structure here. So although it's not QCD, it also may give some qualitative insight into the structure at small omega and small k. So you can also use ADS-CFT to go to larger omega and k, but this I will not discuss. This maybe just a skip. So what we then used is an interpolation of different calculations of the perturbative spectral function, and that is shown here. And we use this at large energies, so above the photon point. So we are interested here at the photon point here. But of course there we wanted to use our non-perturbative result. So we have used this interpolation at large energies and then made an ansatz for the small omega part here, which goes into the correct hydrodynamic regime but has some freedom in the region where we want to extract the physics. And therefore we use the high order polynomial ansatz, which looks a bit complicated, but this is due to the fact that we want to go into the correct limits, the hydrodynamic part at small energies and the perturbative part at large energies, and want to smoothly match this ansatz to those two limits. And we match to the perturbative spectral function at this energy, so well above the photon. And then we use this ansatz to fit the continuum extrapolated correlators now at finite momentum. So for a temperature of 1.1 Tc, you see here the correlators of 3 different momenta compared. So that are the data points here. That's our continuum extrapolation. You can compare this to the best estimate from peak UCD coming from this interpolation. That is the red result here. And it's very nice that our lattice data approaches this perturbative one at small distances. So that shows that at large energies in the spectral function, we become perturbative here. And this agreement with perturbation theory works at larger and larger distances if you go to larger and larger momenta. That's also clear because you go to larger energies in principle. You probe larger energies in the spectral function. But this red curve, that's just the perturbative, and then we use this ansatz with this higher order polynomial and fit our lattice data, and then the result for the spectral function you see here on the right. So the perturbative is the red one, and our fitted one is the blue one, and you see small effects here, non-perturbative effects. If you compare those two, and what we then need is the spectral function at the photon point. So for this momentum, we need just this point, for that momentum, that one, and for that momentum, this one here, to then get the photon point. Also here you see we somehow get more and more perturbative if we go to larger momenta. So here the difference between the perturbative and our fit is relatively small, but here it becomes small. That's the same for 1.3 Tc, and now we can really look into the photon rate. Here in this figure you see the result for the spectral function at this photon point. That is called E effective in our case, and that is then proportional to the photon rate. Here in leading order in QED, but this contains then the full non-perturbative information from QCD. And our results you see here as blue and red points, so for 1.1 and 1.3 Tc. And this is compared to an NLO perturbative prediction, which is shown as a band here. So at large momenta, large invariant masses, we seem to agree already quite well with the perturbative prediction, at least at momenta larger than, let's say, 3 or 4. But the perturbative prediction has obviously the wrong behavior at small omega. So you cannot really trust this, even this NLO calculation at small omega. In principle, this result should go into the electrical conductivity here at small energies, and this here is the result for zero momentum. So in principle, the results should go into this here, while the perturbative goes up. The problem is that we don't have momenta smaller than around 2. This is because for smaller momenta you need larger and larger volumes, and our volumes are already very large. So this will be difficult to go to smaller momenta here, but this is something we want to do in the future, either by going to larger volumes or by changing boundary conditions in the spatial direction. In this way you can also change the momentum. And then to understand how really the non-perturbative part here works, and how these photon rates go at small invariant masses. How much time do I have?
5 minutes.
5 minutes. Okay, then I may skip the next part. So that would be a discussion about heavy quark bound states in the medium, but there in principle we don't have any new results from the lattice. We are working on that by also performing the continuum extrapolation for these correlation functions for charm and for bottom quarks, then to determine spectral functions also for charmonium and bottomonium, and to understand the dissociation temperatures of different charmonium and bottomonium states, and also to determine heavy quark diffusion coefficients. That is something that I will then discuss at some other meeting. This I will skip. So this is a calculation using a complex heavy quark potential determined from a lattice calculation and then used in a Schrödinger equation, not for the wave function of the heavy quark bound state, but for this correlator. And then there we have determined the spectral function in the region of the bound states. Maybe just some information about the results. So this is at 0 temperature for, what is that? That should be the vector, I guess. The charmonium vector. So here you see the J psi, you see one excited state, and then you get the continuum here at 0 temperature. Then if you switch on temperature, some of these peaks become broader, you get some thermal effect. You also see a mass shift of these states, so once they become broader, they also seem to decrease in mass. So this happens first for the excited states, but also a bit for the J psi here around Tc. Then if you go to higher temperatures, then the excited state at some point is gone, and you may have still a J psi, which then gets broader and broader, and some temperature goes away. The same, well, I will speak this. Same we also calculate for bottomonium and for p-wave states, but there's no time to discuss it here. I will just briefly go into this calculation. That's a bit different calculation where we wanted to determine the heavy quark diffusion coefficient, but not using this correlation function here, but we took the limit n to infinity in principle and used heavy quark effective theory, where you can expand this correlator here in terms of the quark mass or the inverse quark mass, and then you will get a correlator which is no longer a mesonic correlator like here, but it describes a single quark in the medium which gets hit by color electric fields. So that are these color electric field insertions that you see here. In principle, it's a Polyakov group which gets this color electric field insertion at two points in space, in time. Sorry. So this operator and the corresponding transport coefficient, which is the heavy quark momentum diffusion coefficient, you can calculate also in perturbation theory. But there you see a very poor convergence. You go to very small couplings to really see that the series converges, while for interesting couplings, it's not clear what happens here, so you don't really see a convergence of the perturbative theory. But nevertheless, perturbation theory also is very useful here, because you can calculate the spectral function and then use the large omega part of the spectral function, which should become perturbative as an ansatz again for describing the lattice data. And the lattice data for this correlator you see here. We then have performed, here we even used 5 different lattices and then performed the continuum extrapolation. And then used an ansatz now coming again from perturbation theory, that's here, which then goes rather smoothly into the limit omega to 0. So we have here then the transport contribution. For this operator, there is not expected that you see a transport peak, but a rather smooth behavior at small omega, and that's why we are so interested in this operator, because somehow it's easier to determine transport coefficients from this operator. And then we have used this ansatz and again used different models in the infrared to to fit our correlator. And, two examples you see here, but you don't see a difference in these different models. So in the spectral function, all these models that you see here, they all describe our data perfectly. So that's somehow again the uncertainty that we have in the spectral reconstruction, while you have a perturbative part in the spectral function. And then we used all these models that we had, where we used different Ansätze or different polynomials in the infrared part to estimate this heavy quark momentum diffusion coefficient, and the results you see here. So they scatter a lot, but nevertheless we could give some estimate, some continuum estimate for this kappa, which still has some quite large range, but at least we have a lower and upper limit for this transport coefficient, which is related to the heavy quark diffusion coefficient D through this relation, and you get these numbers here. And you can use this to estimate the time scale that is associated with the kinetic equilibration of heavy quarks in the medium. That's done here. And if you put in here realistic quark masses like, let's say, for charm, you would see that close to TC, this kinetic equilibration time is of the order of 1 Fermi over C, and therefore charm quark kinetic equilibration appears to be almost as fast as that of light partons. And that may be one indication why you see this flow of charm quarks that we have seen in the experimental lectures and also I guess some posters. So that brings me to the end, and I will just flash you my conclusions because I think I said everything on that. The next goal is to do continuum extrapolation for charm and quantum correlators in the same way as I explained for the light quark case, to really then understand also the effect of dynamical quarks. Especially when we go to closer to TC, the effect will be quite large. Not mainly due to these diagrams, but due to the change of the phase transition. So in this pure gauge theory, we have a first order transition, while in full QCD we have a crossover. So things might be a bit smoother at the crossover transition. And therefore it's really important to do full QCD calculations. But this will keep us busy, I think, for the next 10 years or so. So stay tuned for the next slides. Thank you very much.
Good. So thanks for this good lecture. And then any questions, or did everybody realize that, oh, this is clear, no further questions? Okay, Rob?
I'm just going to expect that what would be part of the group from first principles, the shear viscosity.
The shear viscosity. That's difficult. Well, in principle, one can do the same business also for the shear viscosity, so then calculate correlators here for the energy momentum tensor. But the problem is these gluonic observables are very tricky. They have large fluctuations, and you have to use so-called noise reduction techniques to get a signal for these correlators. We will try this in the future. We have already started working a bit on that by, for instance, using this Wilson flow to improve also on the signal. And also combine this with other methods to get correlation functions. So the big problem there is really to calculate the correlation functions in a very good quality. So you need errors. The errors that I showed here for our correlators, they are of the order of 1% or even less. And you really need this for the spectral reconstruction. And at the moment, it's not really possible to do it with standard techniques for the energy momentum. But we will try that in the future.
I guess my question is, do you need a better insight into the spectral functions? Is that what's necessary, or just to beat down these?
Both. You need very good correlators, and you need a very good ansatz for the spectral function. So there also you need perturbative information in the UV. There also less is known compared to this case here, but people are working on that. People are working at least on the NLO part, also for the shear and bulk viscosities. So I guess in the future we hopefully can combine good lattice data with better perturbative spectral functions to also tackle this important.
David?
You compared your results basically with perturbative schemes for the larger temperatures for energy, and have demonstrated that there's some variability in the low energy to non-perturbative sector. Is there some guidance from non-perturbative models like non-Lazinum or Dyson-Schwinger equations?
Well, then I guess you know better than me.
Yeah, but I have not yet concretely.
Yes. Well, for the low omega part, I don't know.
Yes, there is.
There should be, but the question is, well, of course it would be interesting to also test these models. So therefore, I think it's an important question. Of course, one can use our legislator and then use these models in the region where they are valid and try to describe our data. It's of course a very important thing to test the models, but also maybe to understand the non-perturbative part of our spectral function in a better way.
I think in this context, we have a phenomenological results on the low matter spectral function. So we actually know what is the scattering length, the medium scattering length at this chiral crossover temperature, calculations of Bamba and Ra. So you could take, I mean, just compare, because you are very close to TC, you have 1.1 TC, so you could compare, omega going to 0 is just the scattering length, so you could calculate and compare the scattering length from these calculations with the phenomenological results, and choose one of these extrapolations which you have heard, and this would decrease your systematic errors.
Yeah, that's right. I think this will become very important if we go to full QCD and if we get even closer to TC. I think here in this quench medium we never saw any signal of a bound state, of a row resonance or whatsoever. So these correlators that I showed you here show a very perturbative behavior, let's say, or close to perturbative behavior. I think this will change if you go to full QCD and maybe even at these temperatures, but surely if you go closer to TC, and even if you go below TC, of course, all these models will become important. And the big question there is, of course, what happens to the row and other states, does it broaden or whatsoever.
I mean,
And that will be something for the
we
future.
have
But
not
we need full,
any further questions.
but we need full
further
QCD
comments.
for that.
So it's time to thank Olaf again. And we have a coffee break of 24 minutes.
so long.